Afternoon. I'm Candice Pearl. I am a PhD student at the JKMRC in the flotation chemistry group. I'm about midway through my PhD, which is on using collectors dosed as an aerosol to improve the recovery of coarse particles. My supervisors is Lisa Forbes is my primary supervisor. An excellent specialist in flotation chemistry, with co-supervision by Lisette Verster and Professor George Franks from the University of Melbourne. Okay, so let me get into this interesting topic. But before we do, just a little bit of background on why this particular topic is important. So I'm sure everyone is aware of the enormous amount of metal we need to produce for the clean energy transition. And in order to do that, if you look at the chart on the right, it's pretty clear we're not currently on track to produce all those metals with our current levels of production. So we're going to have to ramp up mining production significantly in the next few years. Unfortunately, our current mining methods have an extremely high environmental footprint. So if we're going to continue with that high environmental footprint, whilst significantly ramping up mining production, the benefits of transitioning to clean energy may well be outweighed by the harm that mining is going to cause. So we need to do something differently. We need to decrease mining's environmental footprint. And that's where coarse particle comes in. Coarse particle flotation comes in. This is a different way of floating the valuable minerals we need. And the benefit it offers is primarily through reduced energy consumption for comminution, but it also provides a host of other benefits, like early gang rejection. Your downstream equipment will be much smaller. You're producing a coarser product out of your plant, so you've got different options for tailings management, like dry stacking. You've got better options for recycling water. And then obviously you reduce the use of your consumables, like chemicals, grinding media, all the other things that come with operating a large mining operation. Unfortunately, using our current technology, coarse particles don't really float very well in conventional flotation cells. So why is this? Well, primarily for there's two reasons coarse particles don't float well. They've got very high mass and they're poorly liberated. The high mass means they're easily detached from bubbles, especially in the turbulent environments that are the conventional flotation cells. Exacerbating that problem is the fact that they're poorly liberated. So there's uneven collector surface coverage because the collector's attached to the valuable sites, but for the coarse particles, most of the particle is gangue. So we've got the problem here where the coarse particles need to be more firmly attached to the bubbles to float well, but because of their poor liberation, they're not as hydrophobic as the finer particles. So in the last couple of decades, technology has been developed to take care of the easily detached problem, and this technology being fluidized bed flotation. So the environment we float here it's a quiescent environment. So flotation occurs in the tightly packed fluidized bed. Doesn't have a lot of turbulence, but you've still got the very close contact between the particles and bubbles, which is necessary for flotation to occur. In the hydrofloat fluidized bed flotation machine, additionally, you don't have a froth zone, which is also hugely beneficial for coarse particles. So we've got this radically changed hydrodynamic environment that is particularly well suited to coarse particles. But what do we do about the hydrophobicity problem? Because this particular problem still remains. And as the particles get bigger, you need them to be more hydrophobic in order to float. If you look at this chart I've got on the right, we can see that for the two different flotation machines for your conventional cell, on the far right, you need a significantly higher critical contact angle, which is analogous to hydrophobicity, to float than in the hydrofloat machine, which is the more quiescent environment. Nevertheless, with increase in particle size, your contact angle still increases. So that's the problem we want to address. And how can we do this? Well, quite simply, we could increase the collector dosage, or we could use designer collectors, which would effectively improve the particle hydrophobicity, but it comes with problems. If you increase your collector dosage, that's going to have a negative impact on your selectivity. And then the higher dosages and designer collectors are also significantly more costly, not to mention the environmental impact of using more chemicals. So we need to be creative and exploit the thermodynamics. We are chemical engineers after all. So bear with me for the next 2 slides. It's only 2 slides of equations, which I'm going to use to explain what the thermodynamics tells us could be a solution to our problem. So we start out with the Gibbs absorption equation, which relates chemical potential and surface energy. In flotation, absorbing collectors onto the surfaces makes those surfaces become hydrophobic. And in our flotation systems, we're always dealing with dilute solutions. So we can simplify chemical potential to be a function of collector concentration, which is this equation I have in the middle. Now, if we substitute that simplified equation for dilute solutions into the Gibbs absorption equation, you can see that at the liquid-gas interface, surface energy decreases with increasing collector adsorption. Now, this is quite useful because in this new Gibbs absorption equation, we can measure those variables. We can easily measure the collector solution concentration, and using a tensiometer, we can measure the liquid surface energy. Unfortunately, this doesn't help us understand what's happening at the mineral surface, because this is for adsorption at the gas-liquid interface. For what's happening at the mineral surface, we need the help of Young's equation, which relates the surface energies at the 3 interfaces. So the solid-gas interface, the solid-liquid interface, and the liquid-gas interfaces. They're related through the contact angle. Now, when the surface becomes hydrophobic, that is, the contact angle is greater than 0, then the cosine of the contact angle is less than 1. So we can rewrite the Young equation to what we have in the middle there, which says that the difference between the surface energy at the solid-gas and solid-liquid interface is less than the surface energy at the liquid-gas interface. Now, mathematically, this can only occur when the surface energy at the solid-gas interface decreases more than at the solid-liquid interface. And from our previous Gibbs absorption equation, because surface energy decreases with absorption, we can conclude that adsorption must be greater at the solid-gas interface than at the solid-liquid interface. Okay, so if you didn't follow all of that, which I've given you a lot of information in a very short space of time, go read that paper at the bottom. It's a very good, very interesting paper, and it explains all these concepts very nicely. But what does this all mean? So traditionally, we dose flotation reagents into the pulp as a solution, where absorption occurs at the solid-liquid interface. However, as we've just seen, thermodynamic theory predicts that adsorption would be greater if it occurred at the solid-gas interface. And since flotation relies on bubble-particle contact, that is, contact at the solid-gas interface, what if we were to introduce the collector on the surfaces of bubbles rather than on the surfaces of minerals? As in, perhaps we should be dosing these collectors as aerosols. Now, aerosol dosing isn't a new concept. It was first studied by Soviet scientists in the 1950s. And there's been a number of studies since then. Most have involved very simple systems, single droplets and particles. There's been some studies with synthetic ore systems in micro and laboratory scale flotation, and a few complex ore at lab scale. All the results have been encouraging, but the studies have been disconnected with not very much follow-up. So here's a sample from some of the studies. Let's see, can I find the pointer? Never mind. So if we look at I'm just going to highlight the study done on a coal system. This is on the bottom left. So two dosing methods were used here. There was dosing the collector as an aerosol continuously into the flotation system, and then dosing the collector continuously as a solution into the flotation system. So you can see initially the recoveries were similar, but the final recovery, the aerosol system produced a better recovery at lower ash grades. And then if we look at the study on the bottom right, this was done on a complex copper ore. And once again, the aerosol system or aerosol dosing and with the collector dosed as a solution. And here we see both higher recoveries for the aerosol system as well as significantly better selectivity of the copper mineral over the pyrite. So this is what's been done in the past. There hasn't been terribly much done recently, so this is what I'm aiming to change with my work. But before we get into results, how do we practically go about creating this aerosol? Well, this isn't a new concept, but it isn't common practice, and there is no uniform methodology on how to do this. Of the studies that have been published, they've used a variety of techniques, but none of them are very well described, and there's not much detail given. So it would be difficult to replicate what's been done in the past. If we look more broadly at what's been done in the minerals industry for options that already exist, intense mixing of gas and liquid is not all that new. The Jamison cell probably being the example that springs to mind first. Unfortunately, the scale of the Jamison downcomer is significantly larger than what we need for a reagent dosing application. Outside the minerals industry, atomizers and nebulizers are very common. We've got the fuel injection system in vehicles, and then nebulizers are widely used in a number of food, biological, and medical applications. So yeah, we're at the point where we need to develop our own methodology, since nothing suitable exists at this point. So what are the requirements for that? Well, firstly, we need to ensure that whatever we use is safe to use. Mining chemicals can be quite harmful to one's health, and aerosolizing them and introducing them into the breathable atmosphere is potentially a severe risk. Secondly, we're doing science here, so we need to be able to produce viable results that are reproducible. And then finally, we want whatever we're using to be easy to use and potentially be able to be scaled up to full scale. So I looked specifically for commercially available options. So we could have built a bespoke system, but that again runs into the problem of any results we produce are not necessarily reproducible by other people. So we looked at the most simple option, which is a Venturi style nozzle, and a nebulizer designed for pharmaceutical applications. So what exactly does this entail? Well, for the nebulizer, for the Venturi, we introduced the chemical into the neck of the Venturi with the air flowing past to produce the fine mist of collected droplets. Now, for lab scale, the biggest challenge for finding a Venturi was finding a Venturi small enough for a lab application. We eventually found quite a small one, and it worked all right. A smaller one would have been better, but they're simply not available. Also, with the Venturi system, we obviously need a means of delivering the chemical into the neck of the Venturi, and for that we used a Watson-Marlow 100 series pump. For the nebulizer, we found a nice off-the-shelf option that sells nebulizers for lab scale and industrial scale applications. What's nice about this particular means to nebulize is it doesn't alter the liquid in any way. It doesn't change the temperature. It doesn't change the pressure. It works by applying an ultrasonic vibration to a ring containing a micro-perforated membrane. So there's no direct contact of the electronic parts with the membrane, which is nice. And that vibration causes the liquid surface tension, when it's exposed to that vibrating membrane, causes a cloud of droplets to form. The other nice thing about the nebulizer is the droplet size is determined by the pore size. So yeah, our nebulizer produces a very fine mist. In our particular case, it produces 5 micron droplets. The company produces nebulizers that can produce anything up to from 4 microns to 60 micron droplets. Okay, so our next step was obviously getting flow calibrations for these devices. This was very easy with the Venturi and Watson-Marlow system. So Watson-Marlow pumps produce those amazingly linear pump curves, which you see on the bottom there. The nebulizer, we didn't know what effect the back pressure from the flotation cell would, what effect it would have. So to avoid that entirely, we constructed our calibration curve attached to the flotation system as it would be for the real flotation test, and timed the length of time it would take to fully nebulize a known mass of water. It didn't produce as smooth a curve as the Watson-Marlow, but it was nonetheless still extremely linear. So yeah, we were happy with our flow rates. And I'm showing here, you hear the two systems actually installed on the laboratory flotation cell. So you can see here, this is all commercially available equipment. Our nebulizer on the left is fitted into a standard PVC fitting with standard gas fittings connected to it. Our Venturi on the right is directly connected to standard Festo gas fittings. So all of this is commercially available, nothing bespoke in our system. Okay, then the next step was actually testing to see that what we're doing is safe. Flotation collectors can be highly toxic, so we don't want to expose the operator to inhaling any droplets that may escape from the system by the top of the froth phase. So we evaluated the potential of this happening by adapting the standard method for fit testing of gas and chemical masks. This is a qualitative test where a bitter tasting solution is aerosolized and the mask wearer is able to detect the chemical in the breathable atmosphere by the presence of a distinct bitter taste, which is, you're quite sensitive to it. So even a tiny amount of the solution can be detected. So how we did this for our actual test was we ran our test at normal test conditions for a flotation test, except instead of aerosolizing collector, we aerosolized the Bitrex solution. And in this case, because we wanted to see that the collector is not escaping the flotation cell, our unmasked operator did their level best to taste this bitter solution coming off of the top of the flotation cell for the full duration of the flotation test, which was 15 minutes. And then finally, as a control, at the end of the flotation test, the nebulizer was withdrawn from the airline and the operator was able to immediately taste the bitter taste once the nebulizer was releasing solution into the atmosphere. So the risk assessment outcome was it wasn't necessary to use a chemical mask when conducting the flotation tests, because we're reasonably sure that the collector is not escaping by the top of froth. Okay, then we get on to the equipment proof of concept. So we know it's safe to use, but does it actually produce a viable flotation test? And are the results reproducible? So to do this, we tested 3 dosing methods. The first one being the conventional way of dosing collector, and then we tested aerosol addition using the aerosolization methods we're evaluating. The objective of this evaluation was to determine whether the methods can produce a realistic flotation outcome, and as well to determine the usability of the methods in both the lab and the potential for scale-up. For the flotation test itself, we used ore sourced from Irish Resources Triton operations. It's got some degree of natural floatability. Our sample size was about 1 kilogram at quite a coarse grind, because we're interested in how the coarse particles float. We did 2 collector doses, a high dose at 5 grams per ton and a low dose at 1 gram per ton. In terms of what the particular dosing methods entail, our batch method is what everyone will be familiar with. You add the collector solution to the flotation cell, you condition it for a period of time. In this case, the period was 5 minutes, and then you begin the flotation test. Now, it's important to note that for the batch test, your collector concentration is at maximum at the beginning of the test. For the aerosol dosing, there's no conditioning time. We disperse the aerosol collector continuously along with the cell's air supply. So in this case, your collector concentration begins at 0 ppm and steadily increases throughout the test, ending at the maximum amount. Okay, so let's have a look at the results. So we definitely did produce a viable flotation outcome with all the methods. The initial recoveries for the aerosol methods were lower than the batch method, and this is expected because for the aerosol methods we begin the flotation test with no collector in the test, and then that steadily increases as we go through the test. For the high collector doses, which are the solid lines, you can see we essentially end at the same recovery for all the methods. The Venturi is a little bit lower, but that could be within the margin of error for the tests. For the low dose, again, we start with lower initial recoveries than for the batch method, but we end off with higher doses for the aerosol recoveries. If we look at the grade recovery curves, as we see for the previous curves, there's a much narrower recovery range for the batch methods. Let me skip back. For the batch method, you can see like pretty much within 4 minutes, it's all over. The test is complete. With the aerosol methods, because the concentration is increasing through the test, we get recovery for the full duration of the test. And we see that with the grade recovery curves. The aerosol methods show much more flexibility to move on the curve, which is not entirely unexpected, because the collector concentration is changing through the test. So I think from this limited set of results, we can definitely conclude that the aerosol dosing methods do produce a viable flotation outcome, but more work is in progress to make determinations about the actual differences in flotation performance. What we can tell from the results so far is that using commercially available devices, no bespoke devices, we are able to produce an aerosol and produce a viable flotation outcome. Comparing the two devices, obviously the Venturi is very cheap, it's very simple, it doesn't have any specific maintenance requirements. On the other hand, the dosing pump is fairly costly. For lab scale, the major drawback with the Venturi is actually finding a small enough Venturi to use in the lab. The other drawback is the uncertainty in the droplet size. So the droplet size is determined by the airflow rate, the Venturi geometry, and the system pressure. Since airflow rate is a very common variable in flotation, if you were to use the Venturi in your flotation test work, that may be introducing another variable that you need to account for, the change in droplet size. The nebulizer is significantly more expensive than the Venturi. For lab scale, you don't need a pump. So for lab scale, the Venturi and nebulizer probably end up being about the same cost. For industrial scale, you do need a pumping system. So for industrial scale, the nebulizer would be a much more expensive capital option. From an ease of use point of view, the nebulizer is very simple to use. It's plug and play. A downside on the industrial side, not very much of a problem in the lab, is the need for good quality water. The nebulizer membrane would quickly block up if you used poor quality water, like processed water with a lot of solids in, or hard water that would form scale on the membrane. On the advantage is you've got a known droplet size that's determined by your pore size, and the operating conditions of your air will not affect that droplet size. So I think overall, for laboratory scale, the nebulizer is definitely the preferred option. For industrial scale, you would probably go with a Venturi because it's simple and low cost. However, if droplet size does turn out to be an important consideration, the nebulizer may be worth considering for industrial scale. And yes, I think that is really all I have to share today. Okay, well, I think that's everyone. Thank you for attending.